Let's look at another product of two vectors that we can define. If you recall last time, we defined the dot product. And the dot product was an operation when you had a vector times a vector. The output was a scalar. We're going to define a new operation called the cross product, where the input is again two vectors. So we have a vector cross a vector. And the output this time is going to be a vector. And it's worth noting that we've been working in an arbitrary finite dimensional space, right? In general, we've been working in Rn, right? And we define the dot product in general in Rn, but for the cross product, we're looking specifically when n equals 3. So let's see how we construct the dot product, or the cross product. So let's say we have a plane, we'll call this capital Phi. This is a plane living in R3. And using the dot product, we learned how to explicitly describe a plane via a normal vector, right? And so when we were describing a plane via a normal vector, we were taking for granted that we knew what the normal vector was, right? And so we were starting with a normal vector and then describing a plane. Well, when you come across a plane in the wild, nature isn't going to tell you what the normal vector is. So how can we find a normal vector to a plane given two vectors that lie within the plane? Well, the answer is the cross product. So the normal vector, or a normal vector, right, is going to be the cross product of the two vectors here. So I've kind of spoiled the answer here, but let's dissect what the cross product is. So here, a normal vector would be u cross phi. And I want to emphasize that, again, this is just in when our ambient Euclidean space is of dimension 3, right? So let's give a definition here. And let's assign coordinates to vectors u and v by u1 through un, but n is 3. So let's just say u1, u2, u3 for u, and then for v, we have v1, v2, v3. And so the cross product, we say u cross v, is defined to be the determinant of the 3 by 3 matrix where your row vectors, the first row vector is your standard unit normal vectors, I hat, j hat, k hat. And then the second row is the vector u, u1, u2, u3. And the third row vector is v1, v2, v3. And we could expand this definition because we know how to take a determinant, right? So if we take the determinant of this 3 by 3 matrix, we have in the first component, right, we have u2 minus, u2 v3 minus u3 v2, right? Because we start with I hat, we block out the row and column that I hat belongs to, and then we take the corresponding 2 by 2 determinant of what's left, right? And so if we took the 2 by 2 determinant here, we would get u2 v3 minus u3 v2. And we could do the same thing for j hat, right? And so if we did this, well, you need to add a negative, because if you remember in the definition of the determinant, you have an alternating sign, right? And so this would be u3 v1 minus u1 v3. And then For the final component, we would block out k hat, and then we would have u1 v2 minus u2 v1, right? And so this will be the vector u cross v. So when I describe this in kind of an abstract setting or with undefined scalars, u1, u2, u3, et cetera, et cetera, et cetera, it just kind of seems like abstract nonsense. And so to really understand it, let's do an example here. Let's say we want to take the cross product of u, which is the vector 1, -1, 2, and v, which is the vector 3, -2, 1. So let's set up u cross v. We know this is the determinant, and because mathematicians are lazy, I'm going to shorten the notation to just bars to represent the determinant. So we set up the 3 by 3 matrix ijk in the first row, 1, -1, 2, and then 3, -2, 1. And we take the determinant here. We're going to have -1 minus a -2, which would be -1 plus 4, which should be 3. And then for j, we have -1 minus 6, so that would be -5, which is +5. And then for k hat, we have -2 minus -3, so we would have -2 plus 3, which should be 1, right? And so here's an example of computing the dot product, or the cross product, excuse me. If you'd like to be more explicit, you can, like we did in Calc 3, you could write this out component-wise. So for I hat, we would have -1 minus -4 I hat, plus for j hat, we would actually have a minus 1 minus 6 j hat, plus -2 plus 3 k hat. And then for that, we would have -1 plus 4 was 3 I hat, plus 5 j hat, plus k hat, right? And so I went over this again just to be a little more explicit here. Now that we've kind of understood the cross product through an algebraic or analytic lens, let's understand what the geometry of the cross product is. So if we have the cross product of two vectors, u and v, we know the resultant vector, u cross v, is a vector perpendicular to both u and v. But you could ask yourself, well, for a plane containing u and v, there are kind of two directions of a normal vector. In the coordinate system that I've defined here, where yz is the yz plane is on the board, and then x is, or on the screen, and x is out of the screen. In this setting, u cross v would be pointing quote unquote up, but you could say, well, there could exist a normal vector that points down. And that's absolutely true. So how do we know which direction the cross product is pointing? And how we determine that is based on the right-hand rule. And so what is the right-hand rule? If you have two vectors, u and v, and we want to determine kind of the direction of u cross v, what we do is we take our right hand and we point our right hand in the direction of u such that our palm is facing towards v. And by facing towards, I mean in the direction of the interior angle, which is an angle between 0 and pi, right? And so in this example, I'll draw myself as a stick figure here. And then I'll try to draw my hand. you can see why I got a D- in 7th grade art here. And so here's my hand pointing in the direction of U, and then you curl your fingers in the direction of the vector V. And then the direction that your thumb points is the direction of the cross product. So in this example, U cross V would point, quote unquote, up, right? What if we were to take V cross U? What would happen if we switch the order of the cross product here? Well, we point our hand in the direction of V such that our palm is facing towards U. We curl our fingers in the direction of U, and then our thumb points in the direction of the cross product. So in this example, V cross U would point in the opposite direction of U cross V, right? Or it would just be a pi rotation of U cross V. And just understanding the geometry of this operation leads us to an important property. This idea that if you switch the order of your cross product changes the direction of your normal vector is a geometric description of anti-commutativity. So we have U cross V is equal to negative V cross U, right? And so this is anti-commutative, meaning if you switch the order, you also pick up a negative sign. Let's go through some more properties here. We also have that if you take the cross product of a vector with itself, you get 0. And we'll come back to this property in a little bit. Once we develop some more intuition of the geometry here, we'll have a better understanding for why this is true. We also have the property that wherever you place a scalar is intrinsic of the result of a cross product. So let's say we have a scalar k. So we'll say k is an element of the reals here. And then we have k times the vector u. So we have ku here, which is inferior to k state. So we take ku cross v. This is the same as k scaled by u cross v, which is the same as u cross kv. We also have a distributive property. We have the property that the cross product distributes over vector addition. So if we had u cross v plus w, this is the same as u cross v plus u cross w. We have an analogous property if you flip the order here. So let's say we had u cross v, u plus v, and then cross w. Well, this is the same as u cross w plus v cross w here. And it's important that we distinguish these properties. You may say, well, of course, right? If it works in property 4 here, then property 5 should be trivial. But it's not trivial since the cross product is actually anti-commutative, right? And so I would challenge you to try and prove some of these properties using just the description of the cross product based on it being defined as the determinant of the appropriate 3x3 matrix. Okay, so I think it would be productive to break here because we've studied more of the algebraic and analytic side of the cross product. And what I would like to do in the next video is understand the geometric side, right? Like, what does the cross product do for us, right? What can we learn from the cross product? And so what I'll do in the next video is explore more of the abstract geometric side of the cross product.